Metamaterials are artificial materials engineered to have properties not found in nature. They are created by structuring materials on a sub-wavelength scale, much smaller than the wavelength of light or other waves they interact with. This precise arrangement of building blocks gives metamaterials their unique electromagnetic properties. Functional metadevices take this concept a step further. They are designed to perform specific functions, going beyond just manipulating electromagnetic waves. These devices hold immense potential for revolutionizing various fields. These include telecommunications, sensing, and energy harvesting. Their ability to manipulate light and other waves at the nanoscale opens up unprecedented possibilities for creating smaller, faster, and more efficient devices. Functional metadevices are not just a theoretical concept. They are an actively developing field with tangible advancements and real-world applications already emerging. As research progresses, we can expect to see even more innovative uses for these fascinating materials in the future. One of the key features of functional metadevices is their ability to be tuned and reconfigured. This means their properties can be changed on demand, adding another layer of functionality. This dynamic control makes them adaptable to various applications. It paves the way for the development of smart materials and devices that can respond to their environment in real time. A key aspect of functional metamaterials is their tunability and switchability. This means their properties, such as their response to light, can be altered in real time. This dynamic control is achieved by incorporating materials with properties that can be externally manipulated. One such material is vanadium dioxide, or VO2. VO2 is a phase change material that transitions from an insulator to a metal when heated. Incorporating VO2 into a metamaterial allows for thermal control of its optical properties. Semiconductor materials like indium tin oxide, also known as ITO, play a vital role. ITO's conductivity can be altered by applying an electric field, enabling electrical tunability of metadevices. Another approach involves using graphene and carbon nanotubes. These materials exhibit remarkable electrical and optical properties that are highly sensitive to external stimuli. By integrating them into metamaterial designs, researchers can create devices that respond to changes in electrical fields or optical signals. This responsiveness opens up opportunities for developing sensors, modulators, and other active optical components. The use of liquid crystals adds another dimension to tunable metamaterials. By applying an electric field, the orientation of liquid crystal molecules within a metamaterial can be controlled. This reorientation influences the material's overall refractive index, effectively tuning its optical properties. This approach is particularly promising for developing displays, filters, and other devices that require dynamic control of light. Microelectromechanical systems, or MEMS, nanoelectromechanical systems, or NEMS, and micro-nanofluidics are revolutionizing the field of metadevices. MEMS and NEMS involve miniaturized mechanical structures that can move and interact with their surroundings at the micro and nanoscale respectively. By integrating these systems with metamaterials, researchers can create devices with unprecedented control over light and other waves. MEMS-based metadevices can achieve dynamic tuning by physically altering the metamaterial structure. For example, tiny actuators can be used to change the distance between metamaterial elements, modifying its resonance frequency. This mechanical control enables real-time adjustments of the metamaterial's optical properties. NEMS offer even greater precision and sensitivity, allowing for the manipulation of metamaterial elements at the atomic scale. This level of control opens up exciting possibilities for developing ultra-sensitive sensors and highly efficient energy harvesting devices. Micro-nanofluidics, on the other hand, deals with the precise manipulation of fluids at the microscale and nanoscale. By incorporating microfluidic channels into metamaterials, researchers can introduce liquids with specific optical properties into the structure. These liquids can be controlled by external stimuli, allowing for dynamic tuning of the metamaterial's response to light. This approach is particularly promising for developing sensors and switches with high sensitivity and fast response times.